Electric boundary conditions. If an electric field is existing at a boundary separating two different media, so in that case, some conditions the electric field should satisfy crossing that boundary. So that conditions are known as boundary conditions. If we have two medias and there is a boundary existing between these two medias, so in that boundary there is electric field is existing. So in order to move from the one media to other media, so there should be some conditions at the boundary this electric field should satisfy. So that are known as the electric boundary conditions. And this boundary condition is helpful for finding the electric field in one region if the electric field in another region is known. And here we have considered three different medias for deriving the electric boundary conditions. The first media is dielectric and dielectric media. Dielectric one is epsilon R1 and second dielectric is characterized by epsilon R2. And second case is one side is conductor and another side is dielectric. And third case is one side is conductor and other side is free space. And in this case also, for deriving all these conditions, we have two governing equations we have. And the first one is from the electrostatic field, that is closed integral E dot dl is equal to 0, and second is from the Gauss's law, that is closed integral D dot ds is equal to q. So we can consider the first case, that is dielectric boundary conditions. So in that first medium is dielectric medium 1, this characterized by epsilon 1, and second medium is characterized by epsilon 2. So in the first media, the electric field E1, and the second media, this electric field is E2. And this E1 and E2 both are decomposed into one tangential component and one normal component. So we can write E1 will be equal to E1 of t plus E1 of n, and E2 will be equal to E2 of t plus E2 of n. Now we consider the equation, that is closed integral E dot dl is equal to 0, and we apply this condition to this closed path A, B, C, D, A. This is a very small closed path in the boundary. Okay, and if we consider this closed path, we can write starting from A, this A1 of t into dl is the length, that is here it is delta w. This is very small length, that is here written as delta w, and this h is delta h. This small region we are considering, a small path. So we can consider starting from A, E1 of t, that is tangential component of this electric field along this length AB, that is E1 of t, the length is delta w. Then the downward direction of this E1 of n is upward direction is shown here, that is taken as positive direction, but here it is the direction is from B to C, so that is downward, so that is taken as minus E1 n, and up to this is delta h by 2, so it is delta h by 2. Then minus from this boundary to this C, it is E2n into delta h by 2. Then from C to D, it is again tangential component of E2 of t, so that is in the reverse direction of this E2 of t, so it is minus E2 of t into delta w. Then again from this to this boundary, from D to this boundary, that is plus E2 of n into delta h by 2 plus this this from the boundary to this point A, that is E1 n into delta h by 2. So the path is closed now. So this, according to this, closed integral E dot dl is equal to 0. The whole path, the electric field is 0. Now if we consider this delta H is very small. In the closed path, this delta H is very small. So we can consider this delta H is tends to 0. We can consider this delta H tends to 0. So the terms in the delta H, whole terms delta H comes to 0. So we can cancel the terms of delta H. This delta H, this term tends to 0, delta H, this also tends to 0, this also tends to 0, and this also tends to 0. So the remaining is E1 into delta W, then this minus E2 of t into delta W. So we can write E1 of t into delta W minus E2 of t into delta W, which is equal to 0, or we can write that E1 t will be equal to E2 of t. So this is the first condition in crossing the boundary. So keep it as equation number 1. This is tangential component of the electric field across the boundary will be same, or E1 t is continuous across the boundary. This is continuous. E1 t is continuous across this boundary. And again we know that in case of flux density D, that is D is equal to epsilon E. So the C1 of t, this D is also composed into two components. D is equal to dt, tangential component, and normal component, dt and dn. So instead of the C1 of t, we can substitute d1 of t by epsilon 1 for the first media, and which is equal to d2 of t by epsilon 2. And this is another condition. So in this we can say that the flux density component, tangential component of the flux density is discontinuous across the boundary, or it may undergo some changes across the boundary. And this is another condition for the flux density. Or this we can say that dt is discontinuous across the boundary. Now we consider a cylindrical surface. So here we have a cylindrical surface, and this area is delta S, and this at the boundary the height is delta H. And here we can consider the flux density is composed into two terms, tangential component and normal component, in two different medias. So we already know that what is rho of S, that is charge density rho of S, is equal to delta Q by delta S, or we can write that delta Q is equal to rho of S into delta of S. Okay. So if we apply the Gauss's law to this closed surface, so if we consider according to Gauss's law, we can write, so consider the closed surface. If we apply the Gauss's law on the top surface, it is, we can write as closed integral d1 dot ds, that is for the top surface. Then bottom surface, that is closed integral d2 dot ds for the bottom surface. And along the sides, along the two sides, so that is we can take it as sides, that is d1 dot ds by 2 is d1 dot ds by 2 plus other side is d2 dot ds by 2. So when we consider the sides, we know that the cylinder area is, we know that 2 pi into r into H. This is for the area of the cylinder. So this delta H tends to 0 means this along the side, this area becomes d1 dot, this area is 2 pi into r into h by 2. H tends to 0 means this term tends to 0. So along the side, this total closed integral d dot ds by 2, this will be 0 when as delta H tends to 0, this integral, the third integral, tends to 0. So the remaining is, here we have this d1 into this closed integral ds, that is delta S. Then here it is minus bottom side, so we can test minus d2 of n into delta S, and that will be equal to total charge delta Q. So again we can take it as, because it's d2 of n, we take it as positive side, positive direction is in the upward direction, but in our case at the bottom surface, this d2n is acting downward direction, so that's why this negative sign comes. So we can write d1n of n into delta S minus d2 of n into delta S will be equal to delta Q. Or again we can write that d1n minus d2n will be equal to delta Q by delta S. But we know that what is delta Q by delta S? That is rho of S. So we can again write it as d1n minus d2 of n will be equal to rho of S. That is equation number 2. Now for a charge-free space, for a charge-free region, we can say that rho of S will be equal to 0, or d1n minus d2 of n will be equal to 0. And this is also another boundary condition, so keep it as equation number 3. So in that, when we substitute the value of electric field intensity, we can say that epsilon 1 into E1 of n minus epsilon 2 into E2 of n, which is equal to 0. Or again we can say that epsilon 1 E1n will be equal to epsilon 2 E2 of n. So the electric field, normal component of the electric field is discontinuous across the boundary, and it may undergo some changes. This is electric field, normal component will be discontinuous across the boundary, but the flux density will be both are equal in the two medias. D1 and normal component of the flux density will be equal in the two cases, in the two medias. This is only for the charge-free region. Now, in order to find the refraction of the electric field, so the same figure. So here is E1 of t and D1 of t is the tangential component of the electric field and flux density. E1n and D1n shows the normal component of the electric field intensity and electric flux densities in the two sides. 1 is represent for the first media and 2 is represent for the second media, and theta 1 is shown here. And if this is theta 1, we know that this angle is also theta 1. So if you take sin theta 1, what is sin theta 1? That we will get as this opposite side is E1t and the hypotenuse is E1. So E1t by E1. So we can write that E1t is equal to E1 sin theta 1. And similarly for theta 2, this angle is, if we take theta 2, what is sine of theta 2? Sine of theta 2 is e2 of t divided by e2. So we can write e2 of t will be equal to e2 into sine of theta 2. Now we know that the tangential component of the electric field intensities in the two medias will be equal from the equation 1. E1t will be equal to E2 of t. So from this we can substitute E1 sin theta 1 will be equal to E2 sin theta 2. And this we keep it as equation number 4. Now similarly we take cos of theta 1. What is cos of theta 1? We know that cos of theta 1 is adjacent side. So in terms of the flux density, we can say that is d1 of n is adjacent side and the hypotenuse is d1. So again we can write cos of theta 1 as d1 of n by d1. So we can write d1n is equal to d1 cos theta 1. And from cos of theta 2, we can say that cos of theta 2 is adjacent side is d2 of n, hypotenuse is d2. So we can write cos of theta 2 is d2 of n by d2. Now what is d2? d2 is equal to d2 of n into cos of theta 2. Now we already know that d2 of n is equal to d2. d1n is equal to d2 of n for the charge free space from equation number 3. From equation 3 we can say that d1n is equal to d2 of n. So we substitute these values. d1 cos theta 1 will be equal to d2 cos of theta 2. Or in terms of the electric field intensity, we can write that epsilon 1 E1 cos of theta 1 will be equal to epsilon 2 E2 cos of theta 2. This is equation number 5. Now if we divide equation 4 with equation 5, so what do we get? That is, equation 4 is E1 sin theta 1 by E2 sin theta 2, and equation 5 is epsilon E1 cos theta 1 which is equal to epsilon E2 cos theta 2. Now equation 4 by equation 5 we will get tan theta 1 by epsilon 1 is equal to tan theta 2 by epsilon 2. Or we can write it as epsilon 1 is equal to epsilon 0 epsilon r1 and epsilon 2 will be equal to epsilon 0 epsilon r2. So we can write it as tan theta 1 by tan theta 2 will be equal to epsilon 1 by epsilon 2, or we can write it as epsilon r1 by epsilon r2. And this is the law of refraction for the electric field, and this is the law of refraction for electric field. For charge free space, rho is equal to 0.